maybe just motivate it, and then like mention some stuff you did last time.
So Tomislav, one thing that Isaac and I talked about yesterday, Isaac's working on the K framework I can't think of a word that I use all the time. Implementation. Of RowCalc. And so I was thinking it might be beneficial for him in that, and for me in learning Parsec, if I wrote a parser for the same RowCalc syntax and then an evaluator, so we could like compare notes. So one thought I had was, what if we take a look at his syntax? And it's pretty basic syntax because it's just row calculus, not like Rowlang with all of its, pattern matching and joins and all that stuff. And then tried to parse that into, like we could create data types for proc and for name, and
that would be cool.
Like a good thing to do today?
Yeah, sure.
Okay. So I don't know, Isaac, maybe do you want to show your syntax? You have it written up as BNF, right? That's maybe a good place to start.
I do, yeah. I can just give me a second to get GitHub up.
So you want to parse this K framework file directly?
We don't want to write a parser for K. We want to write a parser for RowCalc.
Oh, based on K framework specification.
Yeah, he's just going to show you this
cool.
that he invented from his kit. Does that seem realistic?
Yeah.
So I was thinking of it as basically like we would create a data type called process, and it would have a couple term constructors. One for nil, that's an easy one. One for send, that's parameterized with a channel you're sending on and the message you're sending. One for receive, which is what you're receiving on, the name you're receiving, and the continuation. One for par, which takes two other processes, and maybe that's it. And one for dequote.
Yeah. And if you remember Jake's sample of row calculus in Scala, he made only this data type is it's very simple to just to collect all this information that you mentioned.
Oh, great! Yeah, that's good. I remember that he did it in Scala, but I don't speak Scala very well, so I don't really remember how it worked.
Okay. Maybe you can talk about that. Yeah.
Sure. Yeah.
I got this up. You want me to share?
Yes, please.
All right. You guys see that okay?
Yeah.
Yeah.
Okay, perfect. Yeah, so that's pretty much it. There's not a whole lot. We don't even need to care about precedence or anything, really just starting at, names as being quoted processes. I also have this ID stuff, which we don't really need to worry about. That's just for writing easier tests. And then, like with a process, it's either a nil process, which is, just like a ground term, a send with a continuation, or a receive with a continuation, par, a send, and refine. And then I just have these brackets, which I guess maybe that's not super important for right now. So mostly just the names and processes.
Okay, cool. So do we know where to find, Tomislav, do you know where to find Jake's Scala work?
Yeah.
Oh, in the chat. Oh.
I must find the Jake's gist. I think it's there.
Oh, it's a gist. Yeah, okay. I'll look too. Oh yeah, I think I've got it here. Row.scala.
Yeah, I got it. Yes.
Okay. Oh, nice. Good timing. Yeah, cool.
Yeah, I already started writing some row parser, but I didn't get too far. So.
Okay. Oh, great. That sounds like a fun thing to work on.
Yeah, but we can start from simpler case because I wanted to integrate this in my code that I already wrote for when the Greg has this lecture. So
yeah, right.
Yeah, but my first try was unsuccessful. So
cool. Okay. Do you want to take the share, or what do you want to do?
Yeah. Okay.
Yeah, I'll give you a share.
So. Do you see my screen now?
Yeah.
Is this okay size?
Yeah.
Mm-hmm.
Oh, I just thought of something so basic that I've never done before. I get such bad glare out my window, and I just realized I can close the blind. Dude thinks he can write a parser, can't even close the blind. Okay, so let's see here. Yeah, take us through this.
So the last time, Josh and I was going through like the basics of parser. We implemented the parser from ground up. Mm-hmm. It's a very simple case of how parsing is implemented, but the way it's implemented is almost the same. But we didn't go through all of the functions necessary to all of this implementation of functor, applicative, and monad for our parser, so to be completely functional. So I'm not sure if should we talk about that or we can go more about the real parsec and write some.
So here's my thought, Tomislav. I would like to finish what we started last week. I think that's really insightful. My concern is that I think one should learn how to drive a car before they build their own car, and I'm not sure I know how to drive one yet. You know what I mean? I think it might be helpful to see some use cases, if we use the actual parsec a little bit, and then we maybe next week or whenever the time is right, we return to building our own from scratch once we've sort of seen what the end product is.
Okay. Yeah,
I have this really high level idea, that a parser takes in a string of syntax and then it gives you back an AST. But I don't really know much about how one writes the code that uses it or anything like that.
Yeah.
So when you say that they give you back AST, they give you back whatever you want.
Okay.
So in ideal case, how I imagine writing a raw parser, as Greg was telling us, parsing is almost the same as type checking. So he was telling us that when you parse the syntax, you're doing this three thing for implementing language. When you parse something, you can do the structural equivalence in the same time, and this is like a type checking. You can say, okay, these things in syntax is the same. When you're writing a par A par B or B par A, it's the same thing. Mm-hmm. But when you parsing, that will be two different things. First it will be A, then B. So if you just return AST in a sense of what you see in the string and you just transform it in some data type, okay, this will be like a AST, but you can do the structural equivalence or different things immediately when you're parsing, and you just say, okay, this is like the same. I will not raise the parser exception.
So that makes sense. Is this similar to what they call like normalizing?
I think when you say normalizing, are you thinking about when you make the term in like a normal form?
Yeah, I think that in Rolang they talk about like, yeah, the normal form of the AST, which is something about like, you know, like you're saying, pars are commutative.
I would say that normalizing is rewriting part.
Okay.
Yeah, it's part of the interpreter, but I don't know what that means exactly.
Well,
I think that
the basic use case of the parser is to signal things that happen, like an end parentheses in the current context. Mm-hmm. And then it's your responsibility to do what you want to do when that happens in this context. So, you know, you're going to have functions assigned to essentially events, which are one of the parser rules was met. Mm-hmm. And what do you want to do? Does that sort of answer your question, Jossie?
Yeah, I mean, I think that's interesting. I don't think it tells me exactly what the Rolang normalizer does, but I think we're getting toward that.
But I mean that if some Rolang term cannot be executed like one more step, then it's in normal form. This is why I'm thinking that this includes rewriting, because when you're parsing something, you're not executing in this step.
Oh, so you're saying the normalizer is actually about like reductions?
Yeah.
Oh,
I'm thinking of that.
Wait, I thought the normalized form was like an equivalent way of writing any part expression. Like I have, you know, some term that has like 5 pars or something, and there's like a canonical way to parse that.
You're saying you have more than one canonical way of parsing.
Well, I mean, they're all equivalent, right? So it doesn't matter if I do the first, the second, the third, the fourth, the fifth, or if I do the first, the second, the third, you know, the fifth, the fourth, or whatever.
That's similar to my understanding too, right? So we all agree that A par B is structurally equivalent to B par A, but for the sake of having one canonical way of writing it, we agree that like A par B is the normal one because we're going to alphabetize them or something.
Right. Yeah.
But I don't know if that's
I'm thinking that in that sense, A par B or B par A, it is in normal form, because you cannot reduce it anymore.
Okay.
If you have something that is sending and receiving, and it can be like a com event in this term, then this is not in normal form, because you have all the data that you can reduce even more.
Okay, so normal form is not about like one unique way of expressing like an equivalence class through structural equivalence of terms. It's just about whether or not it can be reduced further.
Yeah, I think that this is correct. Yeah.
Okay. Maybe I thought it was something different than it actually is.
Yeah, same. I didn't know what it was though. So okay, but
yeah, me either.
I think we can carry on wherever Tomislav wants to, though, right?
Yeah.
So maybe we can write some simple expressions, some simple parsing expression for this K specification.
Yeah, that sounds like a cool idea. I'm down for that. So I was thinking it might start with something like data type proc equals nil bar send parameterized somehow bar.
I was looking at the syntax of the BNF syntax of rolling directly, and I was trying to make example of this syntax, but it's like more complicated.
Rolling is complicated for sure, yeah.
It's for this example, it's more complicated, but because if you take any process term in rolling, it's usually recursive. So in a sense that this is also recursive. Mm-hmm. Because this do you remember from last time, this proc is contains definition for this if else.
Yeah, totally.
So when we have these brackets, usually we have some kind of recursion, because this is like a nesting, and there will be some kind of branching.
Mm-hmm.
And with Parsing, you must think about this because when you write something recursive, you must take care of if this is like a left recursion. So if this proc is on the beginning, so you have definition something like this, and this is like complicated things for Parsing to do.
Well, I didn't understand that change you just made.
But I'm using the same parser that I'm defining in the left position.
You're saying if proc if else's can contain proc if else's?
Yeah.
Yeah.
Okay. So this is like recursion, and usually this kind of parsers they cannot do this kind of recursion.
Wait a second.
But maybe better not to go there right now.
Yeah, you're just saying if that you have nested if else statements, right?
Yeah, and if you have something that is that can be self-recursive.
Yeah.
In a sense that you can have the same thing multiple times.
Yeah.
Or this kind of thing.
But right. What did you mean when you typed proc if else right there where your cursor is? I wasn't clear about that. That's not how you parse an if else, right? What you have now is how you parse an if else.
Yeah, but you can say in some kind of a different parser. You can say, okay, I have. Let's see if Roland can have.
Yeah, do you want proc if else on the inside of the parentheses?
Yeah, but I want to write some kind of complicated case when you have this parser immediately follows this kind of parser. So maybe this will be.
Yeah, par is even complicated, right? Because that can just go down forever.
Yeah, and this kind of parser you cannot write directly in Parsing because of left recursion.
Okay, I understand.
It's like a limitation of this kind of parsing.
Interesting. Okay.
Oh, so
but you have different. Yeah.
Even though it grounds out at like nils or something, you still can't do it in Parsec?
Well, you have the ground type, but you're starting parsing. This is like especially complicated if you have strict language, not like Haskell. Haskell is a lazy, but in strict language, this is very, very difficult to write because you are going into the function and you're just going again and again, deeper and deeper.
When you say strict, you mean like evaluation strategy strict, right?
Yeah. Okay. So you're trying to parse this one, and this one gets you to.
Oh, sure. It's just an infinite recursion.
Yeah. But it's easily to write in VNF syntax and just say, okay, this is like.
Yeah, that's the beauty of VNF.
Yeah. All right, cool. So let's try to parse a simple send with the built-in text.parser.parsec or whatever. I forget what it was.
Oh, well, for send. Okay. So. I will include. I'm using this package YAML file. It's easier to write dependencies in Haskell because I can just build with stack and stack will download the dependency.
So what program are you using here?
Sorry?
What program are you using here?
Oh, this is Visual Studio Code.
Visual Studio Code. Okay, cool.
So, Tomislav, I'm trying to keep a list of just like general Haskell stuff that I should look up so that I'm not wasting your time on the basics. So I've already got Cabal on there, and I've got Stackage on there, and I've got Hugel on there. What is Stack? That was something you just used, right?
So the main problem with the Haskell is when you have different version of libraries, because in Haskell you write instances for some kind of for some type class, and when you write instance, you're really saying, okay, I'm writing for this version, but you can have so maybe I'm let's explain to like a simpler way. This stack is created because with the Cabal you're only able to install dependencies for only one version, and the global to your account or your machine.
Oh,
and that's why it's difficult just to use Cabal and just say, okay, I will use different libraries, and because you're I had this problem when I started to learn Haskell, because different libraries use different versions of the same.
Yeah,
the same
totally.
And you can easily just you have different versions, and this doesn't work because you have different instances for different type classes. This is the major problem.
Yeah.
And, and this guy, sorry?
Yeah, I think I get it. Python has virtual environment for this purpose.
Yeah, exactly. And in Node, you have each project have a different folder. But I must say that this is not completely the same thing. Okay. Because different languages have different way of like managing this stuff. But so they created these guys from FP Complete. They created Stack, so they are packaging the whole set of libraries in one Stack version. So when you say here, I'm using this resolver, you're saying I'm using this like one version for all these libraries that exist. And well, not exist, that they put in their LTS package.
Okay.
So.
Yeah, I think that's enough that I get the basic idea.
I only can say that it's like a pretty important. But
okay.
it's not very well, I think, documented or explained for beginners. But you can see here that for some LTS package, I'm not sure what LTS means exactly, but you have many libraries that are included here for each version. So what they are saying is that okay, with this LTS package, all these libraries are working together. So we are saying definitely they're working together, these versions. And this version works with this version of GHC.
Gotcha.
So that's why I'm using this LTS version, not the latest, because I'm using the GHC like globally, because Stack can install their own versions. But my extension for Visual Studio Code works with only one version of GHC. So
okay, all
yeah,
right.
it's just everything is just a matter of dependencies and how you
gotcha
get the correct version. So this is like our module for Parser, and we can import I'm not completely sure. I'm writing different languages, and then I forgot how to write. It's not for all, but it's.
oh, parens
no.
maybe.
No, I must specify first from what I'm importing, and okay, parsing here. Maybe I can just say this like this, so I don't have to import each of the function and each of the data type. So first of all, we have parser. We need to specify our data type. There is a definition for so what I need is the main parser definition. I don't see this here. Because I need to specify like a simpler one. So let me see.
So is it possible to just start with something super simple that correctly parses nil? Like just those 3 characters in that order, NIL?
But I don't remember all the data types for parsing. I didn't use it like for weeks. And
yeah, I see.
Where is my? Let me see here. Oh, yeah, here I have these samples. I did something like this. Because what I need is definition of a parser. Oh, this is already defined here. This is like a string parser that we can use directly. Okay. So we need to specify first a data type that we want to parse. Right. Oh, you're muted.
Yeah, this is what I was thinking was a starting point, right? So this is where we say like the different process constructors.
Yeah, and this is like our AST.
Yeah, right, exactly. Okay, that makes sense.
But we first defined like a basic parts of this the whole parser. So first, first we need to specify these brackets, for example, or no, we want to parse send.
Okay.
Right?
Yeah.
So send is really something like a channel that we are sending, and let's do it like this. And so here we can send like another process, but we can say, okay, let's make it simpler and not recursive. So maybe we can just send a string or something, or
yeah, great,
or number.
Okay.
So let's be simple. So this is like a one string. Then we don't want space here. Maybe better without space, because if we have space, we must specify this in a parser. So we can just say, okay, we have this text, but inside this text, we probably don't want to another exclamation, and then we want to have something in the brackets.
Yeah.
So we can combine. We can see this parser as combined of these different parts. So the first part is like a send name. We can say, okay, this is our parser send name, and he will be parser of string.
Okay.
After that, we need to parse this exclamation. And this will be parser of one char.
Yeah.
So those are the types there that you're doing with the 2 colons, right?
Yeah, exactly. In Haskell, it's like a different. It's 2 colons instead of 1.
Yeah, it's like almost somewhere between B and F and like just the typical colon.
But they're saying that like this is like a small mistake. They should be using like only 1 colon.
Yeah, well, okay. What do they use 1 colon for something else?
No, 1 colon is everywhere else.
Yeah. Well, does Haskell use it for something else though?
Oh yeah. For a list for cons.
Oh, for cons. Oh, why? Yeah. Okay, whatever. You just want to be.
It's other way around. So usually you have 2 columns for cons and.
Right. Okay, I know that's how it is in ML.
Yeah, exactly. And all other languages. Really.
Yeah.
In mathematics, I think it's also.
Yeah.
I'm looking for one combinator. It's called between. So this this parenthesis can be also a parser that we can say I want to parse something in between these two parsers. So we can say, okay, this is parens, and this p parser is we want to see this parser in between. So we can say, okay, between takes between takes open parser for starting. Then it takes close, and then it takes the parser in between.
How are you seeing that from what's up that tooltip? How are you interpreting that?
You mean the type of this function?
Yeah. I guess that's what I'm asking. That's a type deck. That's telling us the type.
Yeah, but it's not shown really very nice. So this is the type. This is the parameters. The first parameter is parser, which will parse like an opening part.
Okay.
Then it will parse this our parser that we want to put inside, and then we'll parse the latest one. I will write these patterns in two different ways.
What was all the SU and M stuff?
So this is when I was explaining last time. We were working only for very simple data type.
Okay.
But without it's not parameterized in really anything only of the type that is parsing. But the real implementation it's like a more general.
Okay.
And you can specify. You have more parameters to this type, so you can specify if you're parsing like a different type of like input type can be different. You should not only parse a string. You can parse like a byte stream, or you want to have this as a parameter.
Oh, that's why. Okay, so SM and T all have to be different types of streams. That's what the type class on the far left is saying. Like S has.
Yeah.
Okay.
Yeah, specify one of these. This specify. This does not specify what should this type be, but what are.
But they're all part of the type class of stream.
Yeah, but on this side, before this double arrow, you're specifying. I cannot find the word.
Is it
constraint? Constraint. You're specifying constraint on this type. And I will show you how this parser type looks like.
Hey, is that double arrow like an anonymous function type of thing?
No.
No. Okay.
This is really constraint. You're saying with this constraint, you're saying, okay, this S, M, and T we must be something that this type are saying that should be. So when you look at the stream, you can see that S can be really anything, but M must be a monad.
Oh, okay.
So you're not saying, okay, S must be something. This is not specified here. This stream type only specified that this must be a monad, and also this is like a dependency that you must. This dependency means that you must from S, you will all know what is the value of the T. And this will make sense, because if you have a string, this will be a char. It's because you have some definition that is some type that is dependent on the other. But I think this makes sense, because when you parse something, you will have one of this.
Yeah, this makes sense. Okay, so I'm seeing from below it stands for stream, monad, and token. And so you're saying, like, if S is a string, that word had just ended with NG, then T is going to be a character, because strings are made up of character tokens.
Yeah.
Okay, cool.
So this parser type is definition where these parameters are already specified. For monad, it's used an identity, and for S we are using string. So we filled these other parameters, and we have only this A. Where is the? We have only this one. It's really our parameter. All the others we already know what it is, because M is identity monad, which is the simplest one. U, what is U? I'm not sure what is U. Okay. And for S we have a string. So
yeah, great.
Maybe if you look on what's
the punchline is those things are there because this is really abstract, but they've already been filled in somewhere that we don't have to care about, and open is what we care about right now.
Yeah.
Got it.
So we first, in this between function, we are first saying, okay, this is like an opening and closing. It's really telling you that this is some kind of like some kind of brackets.
Yeah, got it. So, okay, so you're going to put a left paren there, right? Okay, and then the next thing is going to be, a parser for a single character, and the single character is a right paren. And now the part that tells us how to actually parse a number.
Yeah. And I don't have what? So now I have the problem because I'm using like these general functions that are defined on Parsing, and I'm not saying what are these other parameters, and the error is you are not specifying what are these types, and Haskell cannot conclude what it is. So I will say, okay, this parser accepts parser of something, and it will return parser of something, right? And I can just remove this one because it will be partially applied.
Yeah, so between takes three things, right? It takes the left paren, the right paren, and whatever goes between it, but you're only partially applying it by giving it the left paren and the right paren. And then when we actually use it later to say we're looking for an int between those parens, that's when we're going to give between its third thing. Yeah.
And we know these parens are on each side because parser, but we are not interested to get the value of this parser because we know what it is.
So Tomislav, at first I was wondering, why does between take those three parsers in such a weird order? Why does it take left, right, middle instead of left, middle, right? Yeah. But this is why, because the interest is in the middle, so it's last, so we can partially apply.
Yeah, exactly, and it's convenient. Yeah. Because if you write it on like a bit without this combinator, we can write it only with, if you remember last time, with applicatives. We can say, okay, this is this parser, and we will use like this. So we are saying, okay, parse these characters first, then parse our parser that we will supply later, and then parse the closing parent. And this one means, okay, ignore something on the right, and this one means ignore something on the left, and we will just return this one.
Got it.
And between is defined, I think it's in this way.
Oh, okay. Great.
Well, we can see, really.
Oh, yeah, that's right.
Oh, it's defined in monadic style.
Yeah,
so,
okay.
Maybe it's defined this way just to get to this recursion thing, because if you have a monad, you first you can depend on the previous value, so you are not parsing all thing like statically, because you're passing the first thing, and then you are inside your monad, and then you can do something else, and I think this why it's defined in this way. Okay. So now we have 3 different things that we can define our send parser. And this send parser will be what this parser will return. It will return some our data type, right?
Yeah. So yeah, perfect. Well, there's only one way to do this, I think, right? It takes a chan and a number.
So we want string.
Yeah.
Let's string be a channel, and
for now we're saying an int, right?
Sorry.
For now we're just saying an int. We're always going to send an int.
Yeah. Okay. Yeah. Let's be simple. Yeah. So our send will just return this parser of send.
Oh.
Right. So when we use this send parser, we will just get this send AST.
Yeah.
Does this make sense?
Yeah, I wasn't quite expecting that. I was thinking this was going to be something like parser of string gives back send or something, but I think that makes sense.
But our input is this string that we are parsing. So we are just applying parser to this input string, and we will get this data type.
Okay, that I think it'll make sense when we round it out. So for line 20, do we need to do like exclam equals care of the exclamation point?
Oh, for this one, we just want to parse exclamation point.
Yeah,
right. only one character.
Yep.
So when we want to parse one character, we use a char function. This is like a
right.
char parser. So we can just say this char parse exclamation.
Perfect. Yeah, that makes sense. Okay.
So you're just specifying almost identical as in BNF syntax, but you must follow all of the typings, and yeah.
Yeah.
So for name, we can parse really any number of characters.
Is that what that undefined portion means?
No, undefined it means it's still not defined. It's not a valid Haskell code, but undefined is a valid Haskell term. You can put it everywhere you like, and
it makes the type checker shut up about you have.
Yeah.
Oh,
yeah.
all right.
But if you run it, yeah, it will blow up. So for send name, we are now choosing what we want to parse. What we want to allow, what kind of characters inside this name. So in the
yeah, one easy way to start is to just say letters.
Mm-hmm.
Or if we, I don't know how hard it is to get fancy, but we could say it has to start with a lowercase, or it has to start with a letter, and then it can contain letters or numbers after that.
So yeah, I started something like this is a definition that I wrote directly from BNF of Rolling. This is the definition from Rolling BNF, and I just did what you say. First is a letter. So one character that we allow in our name can be a letter, a digit, or this character or this character.
Yeah.
This is like a one tick. And the whole variable or the whole name, it's combined of these two so it can be this kind of thing or it can be this kind of thing. And I wanted what I wanted to express. So they are saying here you have many letters of digits. So yeah, it can start with these characters, and then can be with many of this one, and it can start with underscore and have some other characters. But I'm using here some because some is one or more, and many is 0 or more. So you're doing the same thing. You're combining a character with many other characters. Like it's very similar, like a list, and this is why I'm using the cons constructor of list here, because I really have here the first character, the first parser is a character, and if you remember, this is applicative. This is just saying, okay, this is another parameter to this function. So let's first see this one. This is a prefix. This is like a cons function in prefix style. So I'm calling this function with these two parameters. This one as the first parameter and this one as the second. So this first one is a parser of character, and the second one is a parser of string. So I'm combining a character with a string, and this is exactly two parameters to cons function.
Yeah, and you're saying that string may or may not be empty, right?
Yeah, because of this definition, I need to have two different way of parsing this one, because they are not allowed. You're not allowed to write underscore. Yeah, you're not allowed to allow. Yeah. So now I remember. So if I put underscore here also, it will parse only underscore without any character after. But this is not allowed, because underscore only underscore is a special character in Go.
Oh. So that's really just saying that underscore cannot be the last character in in this.
Underscore single cannot be single. Yeah.
Because the single underscore is the match anything but don't bind.
Yeah.
Yeah. Oh, it just can't only be a single underscore.
Yeah. So does many mean 0 or more, I guess?
Yeah.
Right. So if you had put that underscore up on top on line 20 where you have a letter or a backslash, if you then put in or an underscore and then many varchars, that would allow an underscore and then 0 varchars, and that's not acceptable. So that's why you have line 21.
So I'm putting another case like an or in the parser.
That or at the beginning of line 21.
Yeah. This or is alternative combinator. So if you defined a type class alternative, you can use this combinator, and this combinator is really easy. It's saying if you successfully parse the first one, this is the result. If you fail to parse the first one, then you parse the second one.
Okay.
It's really just an or.
Yeah.
So I'm using this or to say, okay, if you have underscore on the beginning, you must have some characters after that.
So some means 1 or more?
Yeah.
Okay. Cool. I think line 21 deserves a comment. Don't accidentally match wildcard.
Oh yeah, that's not a bad idea.
Yeah, nice. I know for sure that future Joshi would not have remembered that. That guy forgets everything.
Cool.
All right, good. So now we've got this pvarchar thing.
Yeah.
Or pvar. We've got pvar is what we really want, and that's what we can use for 26, right?
Yeah, exactly. This is like valid name. So yeah, and now we can write our whole send parser. We can just say, okay, first we want to send name to be specified, and we really need this send name. We want to have it in our result. So we will call this send constructor directly, immediately, right? And we need a second parameter to this send function, right?
I'm not really clear on that. Why is send equal to send, and what is the capital S about?
So this send is this constructor. Let me call it constructor. This can be confusing in the beginning when the data type and the data type constructor is the same.
Yeah, I'm with you now. Okay.
It's usually in Haskell you're defining it's with the same name because they are in different scopes. This is a type scope and this is like a value scope, so they cannot be mixed up.
Okay.
So I'm using this send constructor as a function. Function with two parameters, string and int.
Yeah.
And I'm using map because we are working with the parser. So we can not call the send constructor directly with the send name. We are mapping over and creating a parser of this data type. And so the second parameter is our int. And our int is inside the brackets. So we are saying, okay, this is like a parents, and inside we didn't specify our int.
Oh, I bet there's a built-in one.
The Parsec have different already have included some tokenizer default tokenizers. So you can use this tokenizer to for example, you already have included in Parsec Haskell tokenizer. So we can say, okay, from this tokenizer, we will use the number. So this natural means a number. So I will.
Okay, wait, what just happened? Our rowparser.hs just got a bunch more lines, right? How did that happen?
Oh, I was switching to another project.
Oh.
Sorry, this is the code that I started for.
Oh, okay, all right, roger that. Okay.
So I have this. You can see here. I'm doing the same thing. I have a character, and then the true, false, and then the par.
Yeah. Okay. Okay.
And this is like a for new.
Yeah.
So for a number, I'm using this integer parser that is specified in the parsec already. So this is the this is like this tokenizer, but maybe I can show you. Just to show you that you can find it. So here is the language definition. This data type that no. I think it's better looking in the source, but it's not here. So yeah, we have different definitions already that we can use. So for example, what is the correct the string with the quotes? So this is like already implementation for a Haskell parser that it's like that you have in a parsec library.
Okay.
And I want to have something.
Yeah, we saw natural in there somewhere, right?
And it will return integer.
Oh, great.
And you can see the definition. It's really an integer parser, but it's specified as how it should be parsed in Haskell. So if you have some different kind of numbers in your language, you will write your own.
Okay.
But it's easier to just use this one. No. But let me see. What is the correct type? Yeah, I must give him the definition of the tokenizer that I'm using. So I will say here, okay, I'm creating this tokenizer for Haskell definitions. So this function will create a tokenizer for different languages. So you can, if you want to implement parser for your language, you first, I think it's easier to define all of these definitions, and later you can just create it and use it for your parser. So when I want to have this natural, I must say what instance of tokenizer I'm using. Integer is not int, so I will just change this to integer. And we have our parser. Okay, we can use it like this. So to run it, we must use a run function. Let me see if maybe I need some helper function like this. This helper function extracts a result from our parser and just display it, error or result.
Mm-hmm.
But let's first use the real parse function.
What is the empty string?
This is I think this is state or source name. I'm not sure what it is. Oh, source name. Maybe if you're parsing multiple files, maybe you want to specify from which file.
Okay.
It is more general, so this is why I usually have some kind of helper function too, so I don't have to think about all these parameters.
Yeah,
but it should work. I'm not sure what I'm mistaken. Let's. Yeah, if we want to display our send.
Oh, no instance for show, yeah.
Maybe this was not so clear from the last function. Yeah, let's try it again. Okay.
What is the first error? Couldn't match expected type string to T with actual type either string. Okay, so it's something about that either.
I need one more arguments, but I'm not sure. So I'm giving parser, I'm giving this empty string, and I'm giving the string that I want to parse. I'm not sure what is the problem.
So I think parse gives back an either.
But it says that only have two parameters, two arguments to this, but because here I'm giving this parse function a parser, this empty string, and this input, and this input is a string, and this is like a 3 arguments, and I'm giving these 3 arguments to this function also. I have send This is the parser. Maybe he doesn't know what is the correct type. Here, parser of send. Because it's a more general definition, maybe some type is it cannot be determined after the execution, and this is why the run is working fine. So run is working, but we are not parsing correctly.
Didn't parse right, yeah.
Yeah.
Unexpected bang. Oh yeah, we never put line 38. We never have the exclamation mark.
Oh yeah. This is like almost like a type checking, right?
Yeah, yeah.
Because then you know this is like incorrect. So we can put this exclamation on either side of this part arguments to the send. Let me put like this. So this is our function. This is our first parameter, and this is our second parameter. And we are using map and apply because we have a parser, not the real type. We have a box, so we must map over it to execute. And we can put this exclamation on either side because we want to ignore it. So
yeah,
we can,
okay.
The difference can only be if you must put some kind of parentheses around it to say where is applied. So we can say like this, and this means parse the send name first, and after that parse the exclamation, but use only the send name.
Mm-hmm.
And when we say like this, it will correctly parse.
Send constructor Chan 42. Yeah, great.
And we can put it on the other side also.
And then the arrow has to point the other way.
Yeah, because we are saying, okay, first parse this exclamation, and after that, ignore this exclamation, and after that, parse this one. But now we need to put this parenthesis here. Because it will because it's left associate, it will this exclamation will be part of this expression.
Gotcha.
So we can execute this one, is the same.
Yeah, great, same result.
So all of these combinators are really when you want to understand it, you are thinking about the functions and all the types. But when you write a parser, you don't think about all of these things. You're thinking more about how they look like. You know what I've been saying. You know, ignore this one, ignore this one.
Yeah.
And then it's very easy. But if you think about all of the types, it's crazy to understand.
Okay, cool. So we don't need to do this right now because it's getting a little bit late, but I'm just curious, could we have rewritten line 38 in the monadic style with like a do block?
Yeah, let's do it. So use do block to just to be inside the monadic expression. So first, we want to parse send name,
and we want to bind it to something.
Yeah, to our channel, for example.
Yeah, right.
I mean, channel is a variable. So after that, After that, we want to parse our exclamation.
Yeah.
And after that, we want to parse our parents, but inside this, it's our integer. So we have result, or how do I call it?
Message.
And now we have this parents from which we will get this message integer, and now we are returning pure because we must return value inside the monad, and we are returning our send constructor.
Yeah, okay, of Chan message.
So hey, Tomislav, is that so binding the message from that parens natural token parser, is that kind of like you have like an option or something, just taking like the value of the option, just like extracting the inner part?
This one.
Yeah. So is that basically saying like the message is going to be contained within parentheses, and we want to totally ignore the parentheses and just extract the message?
Yeah, because this is the way how we defined this parents parsing.
Yeah. Okay.
This between function will parse this at the start and this at the end, but will not return it.
Yeah.
It will return only what is parsed inside.
Okay.
So here message is only integer.
Yeah.
Although this line will parse like the whole integer in parentheses.
Oh, wait. So that's like parens of some expression in parentheses that we know is has a token of a natural number or whatever.
Inside.
Matching to message. Okay.
Yeah, we are just building. We are just building different parsers of something.
Yeah.
And we are combining these things.
Cool.
We are saying, okay, we will parse string and integer, and then we will combine these two in like a richer data type that contains a string and integer.
Yeah.
So when we say we have a parser of a send, it really means how this parser is combined on different smaller parsers for like at the end this will be parser of a character, one character.
Right. Okay. Cool.
So in this monadic style, we can do different things. We can say, okay, if we can say something here. If Chan is for example, something like this. So we are now dynamically changing our parser. Because we are using monad, we can do that. Do this. We can first parse the channel, then depending on the result of parsing of this first parser channel, we are executing exclamation parser or this parser with the hash. And what this means? This means that we can say, okay, if I say something like this, let's this be another valid character, Chan uppercase.
Mm-hmm.
This makes more sense. So this will parse without problems, but when I write Chan with the uppercase, this is not What?
Oh.
Oh, this is like a correct.
Your then and else cases, maybe.
Yeah. This.
Oh, yeah.
Oh, in Haskell, this is like.
Oh, yeah. Oh, you can spell not equals that way? No, it's slash equals.
No.
That's how
slash.
it is in ML.
Yeah.
No, equal slash.
It's not equals/equals.
I think it's.
No, I think it's slash equals.
Slash
Really?
equal. I think it's slash equal, but.
I've seen equal/equal before too.
Or. No.
Maybe it's backslash equal.
Oh, slash equal. Oh, yeah. I'm using backslash. Okay.
Oh, there we go. Oh, yeah, there we go.
Now when we're at chain, it's. Oh, I'm using the old parser. Oh, must use send m.
Oh, yeah, you gotta use that one, sure. Well, that was the whole problem from the beginning.
yeah, but I wanted to write this way, another way.
Yeah.
So when I use uppercase, it will not parse. But when I put a hash here, it will be okay.
Oh yeah, okay.
And I cannot do this in this applicative style because each of these expression will be executed like simultaneously. So example of this use of applicatives is this guy Simon Marlov built for Facebook spam filters or like detection of spam messages or something like that.
Okay.
And he was but I think not only specifically for this thing, but he was extending the Haskell to this do notation to be aware of applicatives. So this do notation can be transformed in applicative if we don't have this dependency.
Yeah.
So for example, for Facebook, he was explaining that if you get the friends of you have a list of friends and you want to get friends of all of these friends, so you can do this in parallel. You can say, okay, I have applicative. I don't have to specify how I want to get the results. I only specify this by writing something in monadic style or applicative style, and his code can conclude if this is applicative and just do applicatives and not the monad style. So if we write this one without dependency, we can include this applicative do extension in Haskell, and I think it will also work in this case. It will use our applicatives and not the parser monad functions. Although it's written in monadic style, and like this is the why is this abstraction is so like great, you know. You can find out how the code is, what is the dependency of this monadic sequence, and you can execute some code in parallel and some code in sequence. And in Rolling, this is also true. I mean, this four term expression is really a monad expression. This is like a do expression in Haskell. If this is 4, this will be all the channels that we're extracting, and this will be like a body of the for. Is this make sense?
Yeah, I think so.
Like this one. If I put this parenthesis here and these brackets, this for is really a monad. And really all of this channel, because rolling has only one monad, this channel monad, this process monad. So everything is executed inside this process monad.
Yeah.
And in Haskell, this is like without parentheses, and this is like a do keyword, not the for. But in Scala, this is like a totally very similar to rolling. It's really a for and.
Interesting. So you're saying it's like a monad because it wraps some process?
Oh, Greg was explaining this how for is a monad.
Okay.
And how these channels are they're all the same monad, and you are working all the code in rolling is working in this one monad. So you don't have to specify different monads for different things.
Oh.
And I found this similar how FX library in Haskell is also written, and because this transformation between different monads is very complicated, and it can be very if you have if you nest different monads inside different monads, then you must transform between them. So this is why this FX library is created. Maybe this is not the right page, but no. Yeah, this is Douglas final. This is the thing that the Pavel, one of the developers of rolling, had a talk, I think, in Boulder about effects and.
Oh, this dude gave a talk at RCon too?
Sorry?
You said this guy gave a talk at RCon too?
Yeah.
Oh, interesting. I haven't seen that one.
But you know, on what I'm talking about, on Pavel, this guy Pavel, I'm not sure what is the last name. Pavel is the name.
Oh, Pavel, the dev?
Yeah.
Oh yeah, I know who you mean.
He was talking about effects and some. I think that some of the code in Scala is now written with the effects and.
You're saying effects, right?
Effects, yeah.
Like something that has side effects.
It's related to that, but it really means that you don't have to you don't have to transform all of this. If you have values inside different monads, you don't have to transform it, and you don't have to work with this transformation all the time. So you can specify this in different style.
Okay.
Maybe I can find it in the code, if you like. I think I found it in the node code.
Oh, there's a folder called effects.
Yeah, I'm not sure if. Oh, yep. So this is how effects are defined. You parameterized your definition on this monad that you will use in your implementation. So each of these function return value inside this monad that you will be using, this effect monad. This can be anything you want. And how they are specifying. They're saying, okay, we have console IO. This is some kind of specification of our console, and this is like an interface in Java or C#.
Okay.
And each of these function returns this value inside this f. So when you can see here that each of these function returns f and the value inside. So when you implement this console, maybe it's here or I think they're using the task as implementation for the console.
Oh, wow. Okay. Well, I'm a little lost on that, but there was something in there that I wanted to ask you about that. There was somewhere where it looked like maybe they were doing some similar monadic style.
Oh, yeah. Definitely.
Oh, yeah, like that. Yeah. Is that real similar to what we were just doing?
Yeah, this is exactly the same. This is do, this is pure.
Okay. And so
it's completely the same. So this log info, it must return what? Something that is like this monad, and this monad is. So they are building units. So I'm not sure.
Unsafe scheduler. Well, it looks like maybe they're just logging messages.
Everything is in task because this task delay must return task. So all of this term must be a task mode.
Okay.
So this log info must return a task, but if this is like a parameter, it can return. This can be a parameter. What I wanted to explain. Let me see where is the. Yeah. Okay, it's a task. Yeah, a log of task.
Oh.
But this log. How can I easily find where is the log defined? Probably that's so easy. But yeah, this is like the same thing. This is like a monadic style. How this is written. All of this information is like it will be executed one by one, and if any of this line fails, the whole expression will fail, and it will return this failed value, whatever it is. For if this is like a maybe, it will return nothing. If this is like a either, it will return left. Or if it is task, it will return some kind of task error or something. I'm not sure what it is.
Okay, well, that's probably a good place to pause for today. Can you put that code, that send parser stuff on GitHub, and then I can kind of play around with it and be prepared for next time?
Yeah. Okay, I can put the whole repo. So
yeah,
you can
perfect.
Use the stack and.
That sounds great. That's gonna give me a good context to learn like how to use stack and everything too.
Yeah. I can write some kind of like short manual how to. What do you need to?
Yeah, oh, sure. Type this, then this, then this to get where we were, and.
Yeah.
Okay. Awesome, Tomislav. Thank you so much for going through this again. Just like before, very helpful.
I hope it is helpful. I'm not very convinced that I'm good at explanation, but
no, it's discussion is going great, right? Like you're answering all of our questions, and yeah, I think it's awesome.
And I want to join this Scala group when
yeah, I'm really hoping that Dror ends up taking the lead on it. just because, you know, it's good to have that stuff diversified and who's leading. But yeah, I'd love to jump into if he hosts a session. How good are you at Scala?
Well, I'm leaning the Scala code, but I really don't know the libraries, and this is like the biggest problem for me.
Yeah,
because you have this cats library. They are using now the cats, but there is also a Scala Z, and you know, sometimes it's difficult to understand, especially these cats and Scala Z are like confusing.
Have you looked at the code for RSong?
No, I didn't have the time.
As I mean, Ned was suggesting it, and I know Greg suggested it as a model for the app developers. And going over that would be a good way to get into Scala, I would think.
Yeah. I'm trying to find the time. That's the trouble.
Yeah. Speaking of the time, I sure appreciate you giving us some of yours today. And it's getting late, I think, right? 6 or 7 o'clock.
Yeah, almost 6. Yeah.
Cool.
But yeah, it was fun. So yeah, I enjoyed it.
Jim, thanks for hosting and recording again, as always.
Yeah, I got kind of lost. You know, in the old days, using Lex and Yak, it seemed so much simpler.
Well, for me, this is like more complicated because you have different things separate. And with this kind of presentation, you have all of these things combined, and you can do like you can parse something and immediately do all of these other things. That's why this Greg's lecture was interesting for me. And
yeah, so are we? So that reminded me of something. Are we kind of blurring the lines between a lexer and a parser here?
Yeah, totally.
Okay.
This is completely combined. This grammar is. So this is why I was thinking on the beginning, should we specify space or not space? And
yeah, right. Okay.
Because when you tokenize something, you are calculating space, and after that you're not thinking about space. And in this kind of definition, you must say where is the space, because you have only that.
Okay. All right, good. Well, I will see you guys next week, if not sooner. Isaac, I'll see you soon.
Yep.
I'm going to come get my phone, if that's okay.
All right. Yeah, that's fine.
All right.
All right.
Everyone.
Take it easy, guys.
See you. Bye-bye.
Later.